Welcome to today's presentation, Understanding Terminal Unit Acoustics, presented by Titus Chief Engineer Randy Zimmerman. Randy is a lead green associate with more than 30 years of experience in HVAC product development and applications. He serves on numerous AHRI technical committees and represents Titus in various AHRI product section committees and serves on the Technical Committee on Sound. Now let's begin the webinar.
Hello and welcome to Understanding Terminal Unit Acoustics. My name is Randy Zimmerman and I'll be your instructor. I'm a chief engineer at Titus where I've worked for 37 years. I handle most of the inquiries regarding acoustical performance and serve on many technical committees at AHRI and AHRI where HVAC acoustical standards are developed. Now let's look at what we'll cover today. As a leading manufacturer of air distribution devices, our products can be found in many high-profile buildings and sound-critical spaces. In order to properly specify and select products to achieve desired acoustical goals, it's important to understand how they're tested and rated. We also need to be aware of any changes in testing and rating standards in order to know whether the performance data under consideration meets current industry requirements. We need to understand where those noise criteria or NC levels published by manufacturers come from. We'll look at how lining materials, attenuators, and silencers affect sound levels. We'll also learn how to size and select terminal units for the lowest sound levels. And last but not least, we'll look at the proper installation techniques for terminal units. Before we get into testing, there's some terminology to cover. Sound levels are measured in decibels, or dBs. We don't need to know a lot about decibels, but the reference to a very low pressure and a very low power. It's also meaningless to talk about decibel values without referencing the frequency. In order to make it easy to talk about groups of frequencies, the entire audible sound spectrum has been divided into 8 equal bands called octave bands. Each band is defined by its center frequency. So the first band is centered on 63 Hz, the second band on 125 Hz, the third band on 250 Hz, and so forth. You'll notice that the frequency doubles each time, and that puts the 8th band at 8,000 Hz. We'll talk more about octave bands later. Terminal units are sound tested in accordance with AHRI Standard 130. This standard details the test setups that must be used to determine sound power levels for radiated, discharge, and exhaust sound. The testing takes place in a reverberant chamber. This is generally a large open room that's designed for low sound absorption and high isolation. The low absorption prevents sound energy from being absorbed by the environment before it can be measured, and the high isolation provides low background sound levels. The resulting reverberant environment eliminates all directionality from sound. This allows microphones in prescribed locations to accurately measure sound pressure levels. If you were listening closely, you may have noticed that I just mentioned 2 types of sound levels, sound power and sound pressure. It's important to know the difference. Basically, the products we're testing all generate a certain amount of sound energy. This is sound power. It's the total sound energy. It can't be measured directly, but it can be determined from sound pressure measurements in a controlled environment like a reverberant chamber. Sound pressure is what we measure with a microphone, because a microphone is nothing more than a high-speed pressure transducer. So when a product is operating in a reverberant chamber, it's generating a certain amount of sound power, but some small amount of that sound power is being absorbed by the chamber. So the microphone picks up what is left, and we call that sound pressure. Sound pressure is what we hear with our ears. So the difference between sound power and sound pressure is what we refer to as room absorption room effect, or room attenuation. They all really mean the same thing. So how do we determine sound power levels from sound pressure readings? To do this, we need a reference sound source, or RSS. The RSS is certified annually, so we know its sound power output to 1/100th of a decibel in each octave band. We can use this device to determine the room absorption of our test chamber by placing this device in a prescribed location, switching it on, and measuring the sound pressure levels in the room. This device creates known sound power levels, so if we know that it creates 80 decibels of sound power in the first band, but we only measure 70 decibels of sound pressure in that band, we know that the room absorbed or attenuated 10 dB in the first octave band. This absorption is constant and doesn't change with the sound level. We also know that the amount of material and equipment in the room changes the room absorption, so we have to run this test every day to calibrate the room. If anything is added or removed from the room, we must run the RSS again. So how do we get to a sound power level from a sound pressure reading? We simply add the room absorption to the sound pressure to determine the sound power value that we'll eventually publish. If you look at manufacturers' published sound performance for terminal units, you should see 3 different types. Every terminal unit has radiated sound levels. This is the sound radiating from the casing of the unit, including the induction port on fan units. It's measured by suspending the unit inside the test chamber and ducting primary air to the unit with discharge ductwork to exit the chamber. Of course, the ductwork must be heavily insulated or lagged to prevent breakout noise in the chamber. We only want to measure the sound generated by the unit, not the ductwork. Supply units also have discharge sound levels. This is the sound of air being delivered by a damper and/or a fan. It's measured by suspending the unit outside the test chamber and ducting the discharge air to an opening in the chamber wall with a flush termination inside the room. Exhaust units don't have discharge sound levels, but they do have exhaust sound levels. This is the damper noise that travels back to the room from an exhaust unit. The first thing we do when we're testing is to turn off all the equipment, close the chamber doors, and take a background sound level. This sets a baseline for the tests we'll be running that day. Although we know how to subtract background noise from our readings, the best practice is to only take readings that are at least 10 dB over the background level. We know that whenever 2 sounds are 10 dB apart, they're non-additive and the lesser sound will not be heard. The next step is to run the RSS, calibrate the room, and determine the room absorption, and then we can get down to testing the product. I get lots of questions about the way sound tests are conducted. Sometimes people ask to see the actual data sheets from a test if they have some question about our data. For instance, they may want to see the performance of a unit handling exactly 500 CFM with exactly 1 inch of inlet pressure. I try to explain that looking at the data sheets would probably generate more questions than answers. You're unlikely to have data collected under the exact requested condition. It can also be confusing to look at corrected and uncorrected sound levels taken at seemingly random flow rates and air pressures, especially when the air flows must also be corrected back to standard conditions. This tends to create more questions than answers. And here's another frequent question that I get. Are your terminal units sound tested with the dampers wide open? If so, how can I determine the damper noise at various angles of closure for the damper? In order to answer that question, let me explain the testing process. First of all, we determine the airflow range that we'll be testing and select at least 5 or 6 airflows. Then we determine the inlet pressure range that we'll be testing and select at least 3 or 4 pressures. We first take a set of readings with the inlet damper locked wide open at each of our selected airflows. This is what we'll use as minimum static pressure data. Then we put the damper under control and take a set of readings at each airflow and each inlet pressure. This is what we'll use as our pressure data. We then linearize the data and determine the coefficients of a least squares curve fit. Now we have equations to accurately calculate the sound levels for a unit across its operating range for any flow rate and any pressure condition. Now back to the question. Yes, the units are tested with the dampers wide open, as shown here, to determine the minimum delta PS performance. But we also test them in many other positions based on airflow and pressure conditions. It might interest you to know that the noise generated by a damper in a single duct terminal is dependent on the delta PS, or the pressure drop across the unit from inlet to outlet. For instance, a unit with 1 inch of pressure on the inlet, a unit pressure drop of 0.05 inches, and a discharge pressure of 0.25 inches would create sound based on a 0.7 inch delta PS. This same unit with 5 inches of inlet pressure and 4¼ inches of discharge pressure would create the exact same sound level because it is also based on a 0.7 inch delta PS. Here's another question that I get. How much noise does a water coil add to a single duct terminal? I don't see any mention of this in your literature. Well, here's the surprising answer. A water coil actually reduces the sound level of a single duct terminal. It does this by adding pressure drop to the unit, which lowers the delta PS across the unit. So let's look at an example. If we have a size 8 unit handling 700 CFM, the minimum delta PS would be 0.02 inches. If the unit has 1 inch of inlet static pressure and 1/4 inch of downstream pressure, the delta PS across the damper would be 0.73 inches. Now, if we add a 2-row hot water coil, the minimum delta PS increases to 0.32 inches. This reduces the delta PS across the damper to 0.43 inches. This forces the damper to open wider for a given flow rate and reduces the damper noise. In this case, the radiated sound is reduced by 2 NC points and the discharge sound is reduced by 3 NC points. As far as changes to industry standards, there were no real changes for many years until AHRI Standard 880 was revised in 2012. This is the rating standard that tells manufacturers how they should present performance data gathered from tests run in accordance with AHRI Standard 130. Manufacturers were now required to add end reflection losses, or ERL, to the discharge sound power levels of all terminal units. So what exactly is ERL? Whenever a unit is ducted to a room, there's a sudden expansion of airflow that occurs. ERL is created by either expansion or compression of airflow. In this case, the expansion causes a certain amount of sound energy to reflect back to the source rather than enter the test chamber. In the case of a discharge sound test, This means that any sound energy reflected back towards the source cannot be measured by microphones inside the test chamber. So you might ask the question, if the sound isn't reaching the space being served, why do we care about it? Well, first of all, acousticians need to account for all of the sound energy in a system, not just a room. Also, as we'll see later, when estimating room sound levels, there's actually a deduction being taken for ERL. So until this change took place, we have been deducting something that was never being measured in the first place. You might call that double dipping. Well, didn't this addition of ERL require manufacturers to retest their units? No, the ERL change didn't require manufacturers to retest anything. The ERL to be added was to be calculated based on AHRI research that developed the method of determining ERL based on discharge duct dimensions. These were to be added to each reported octave band up to a maximum increase of 14 decibels. Units with smaller discharge dimensions saw the biggest increases, and larger units were hardly affected at all. This sudden change generated lots of questions from engineers and acousticians who suddenly saw dramatic increases in discharge sound levels, even though nothing about the products had changed. You might ask the question, if we had been incorrectly estimating room sound levels far lower than actual for all these years, why didn't we get more complaints? The best explanation is that discharge sound paths involve ductwork and many different sources of attenuation that are difficult to fully account for. This complicates the estimation, but generally works in our favor to lower room sound levels. We also need to look at lining materials and understand how they affect acoustical performance. Of course, terminal unit liners are primarily intended to provide thermal protection from condensation and to reduce thermal losses, but sometimes lining materials can provide an acoustical advantage. When looking at single duct and dual duct terminals, the softer and thicker the lining is, the more sound absorbent it'll be. This can lower discharge sound levels and make optional attenuators more effective. In these same units, harder facings and more dense liners can block or reflect sound. This can result in lower radiated sound levels, but it can also make optional attenuators nearly or totally ineffective. The effect of lining materials can be difficult to predict in fan-powered terminals. Fan-powered terminals are affected differently by lining materials. In general, softer and thicker liners tend to reduce both radiated and discharge sound levels. But what happens with harder facings and denser materials is widely misunderstood. These harder facings, like dual wall or foil-faced liners, eliminate internal sound absorption while increasing the transmission loss through the unit casing. While a fan unit with softer linings tends to radiate sound in all directions, a unit with a high transmission loss casing will tend to become much more directional as a sound source, with sound emanating from the induction port. This can result in higher or lower sound levels depending on a number of factors. Unfortunately, manufacturers who publish performance in accordance with AHRI Standard 880 are forced to report higher sound levels for these harder-faced liners. This is due to the fact that the lost sound absorption, coupled with the fact that the test chamber eliminates directionality, results in much higher radiated sound levels. While these higher sound levels may scare away some customers, others prefer dual wall construction and have learned to live with it. You might wonder how. Well, it's a fairly common practice to use mock-up tests to determine whether a dual-wall fan unit will meet the specified acoustical requirements. For this reason, testing labs often include mock-up rooms that more accurately simulate actual job site conditions, and published sound levels are ignored. Of course, this opens the door to using data that isn't certified and likely couldn't be reproduced outside of the testing facility where it was measured. So how do we read an NC plot? Let's say that we need to determine the NC level of a room. We would typically command the unit serving the space to its maximum design airflow, close the office door, stand in the center of the room, and take octave band sound pressure readings. Then we'd plot them on a chart like this. The spectrum shown here is very typical for a fan-powered unit. You can see that the second band is the critical band and sets the room level at NC 45. If the second band were to increase by even 1 dB, we'd be at NC 46. The non-critical bands simply trail off. You'll notice that the critical band forms the tip of a very ugly spike. That's very typical of fractional horsepower motors turning forward curved blowers. Larger fans, like air handlers, also typically peak in the second band, but they usually have a much smoother shape. Just a bump in the second band, not a spike. Now that we know a little bit about NC charts, it's important to understand how sound levels are expressed in terms of NC. First, we need to look at typical NC levels for commercial spaces. The quietest space is usually a conference room, specified not to exceed NC 30. Then there's the private office, specified not to exceed NC 35. Then there's open office areas furnished with cubicles or open workstations, specified to be as close to NC 40 as possible. And finally, we have utility spaces like hallways, printer rooms, and break rooms that are not to exceed NC 45. The NC level should always match the purpose of the room. Conference rooms are quiet because they're used for communication. Private offices can be slightly louder and still provide a good environment for private meetings or talking on the phone. Open offices are more productive with a higher background sound level because it creates speech privacy for the occupants and helps to eliminate distractions. Finally, hallways and utility spaces can be even a little bit louder than that because they're transitory spaces that people are just passing through. This is an example of a typical terminal unit schedule that I often see. I'm often asked to assist making unit selections to match schedules like this. First off, there's questions to be asked. As you can see, NC levels are shown for both radiated and discharge sound, but we don't really know anything else about the project. For instance, is the ductwork internally lined? Do they have ceilings or exposed ductwork? What kind of spaces are these serving? Usually we're forced to assume that these NC levels were based on AHRI 885 Appendix E assumptions being applied to a particular manufacturer's product that was chosen as the basis of design. But should we be trying to match another manufacturer's performance, or should we be trying to meet the specified sound level for a room? For instance, if these units are all serving private offices specified not to exceed NC 35, does it really matter if the basis of design unit is NC 22 and the unit we've selected is NC 24? They're both far below the designed sound level, and they're inaudible to the occupant. In other words, if you have two sounds that can't be heard, does it matter which one is louder? No, it doesn't. Both units are providing acceptable sound performance. So where do those published noise criteria or NC numbers come from? They come from AHRI Standard 885, specifically from Appendix E. These are the standard sound attenuations that manufacturers should apply to sound power values if they choose to publish NC levels. They should also be the default values found in any software selection tools. This standard also provides sound path data and procedures for estimating room sound levels for many types of applications. So let's look at the Appendix E attenuations for radiated sound. The standard attenuation assumptions for radiated sound levels are pretty simple. There's a deduction for the environmental adjustment factor. This accounts for the difference between an RSS tested in a hemi-anechoic space and an RSS applied in a reverberant chamber. Then there's a ceiling space effect for a 5/8 inch thick, 20 pound per cubic foot mineral fiber lay-in ceiling. This ceiling space effect was developed by a research project called AHRI RP755. It assumes that the ceiling plenum is at least 3 foot deep and unobstructed for a width of 30 feet and has no significant penetrations immediately below the unit. Now let's look at discharge sound. The standard attenuation assumptions for discharge sound are more complicated because there's more elements to include when considering ductwork. As always, there's the environmental adjustment factor. Then there's lined ductwork assumed to be 5 foot long with 1 inch thick fiberglass lining. Then there's end reflection based on an outlet with an 8 inch round neck. Then there's flex duct assumed to be 8 inch round and 5 foot long. Then there's a space effect based on a 2,400 cubic foot room with the listener 5 feet away from the closest outlet. Finally, there's a sound power division based on the number of rooms being served. Just to complicate things, the assumptions for duct size and sound power division change based on whether a unit is small, which is less than 300 CFM, medium, which is 300 to 700 CFM, or large, which is more than 700 CFM. Small units are assumed to have 8 by 8 inch ducts and serve a single space. Medium units are assumed to have 12 by 12 inch ducts and serve 2 spaces, and large units are assumed to have 15 by 15 inch ducts and serve 3 spaces. So here's what that looks like. You can see that there are 3 sets of standard attenuations based on the airflow capacity of the unit in question. This creates different sound attenuation values for small, medium, and large units. Just to summarize, here are the total radiated and discharge attenuations provided by AHRI 885 Appendix E that manufacturers are required to use if they choose to publish NC levels. Do these assumptions accurately depict many or most projects? No, they probably don't. So why are manufacturers required to use these assumptions? Well, they were adopted in 1998 to create a level playing field and eliminate market confusion. Before this happened, manufacturers were allowed to pick and choose any attenuations documented in AHRI 885 when publishing NC values. It was very difficult to compare performance when different attenuations were being used, and some of the assumptions were overly optimistic and intended to provide a marketing advantage. Often these differences could only be determined by reading a lot of fine print and having a working knowledge of Standard 885. So what do I do if I want to select a product for a project with no ceiling? Open ceilings and exposed ductwork are more popular than ever. Most manufacturers have selection software that allows custom attenuation files to be created. For a project with no ceiling, the ceiling space effect will need to be replaced by a space effect. So how do we calculate a space effect? First of all, you might be surprised to note the entire volume of a room creates a space effect that can be applied to each of the units serving it. The software should ask for room dimensions and a distance from the listener to the unit so that the space effect can be calculated. The calculation is rather straightforward. For each octave band, the space effect is equal to 25 minus 10 times the log of the distance from the listener to the unit, minus 5 times the log of the room volume, minus 3 times the log of the octave band center frequency. Of course, most selection programs will do this calculation for you, but it's just nice to know how it works. This table shows various space effects for rooms ranging from 2,000 to 5,000 cubic feet. As you can imagine, in larger spaces, the space effect can be considerable. But what if my project has ductwork that's not internally lined? Then you go into the software and eliminate the attenuation for duct lining. Actual duct dimensions and the number of spaces served can also be input to more accurately determine the discharge NC level for your project. Now let's look at the octave bands again. In our industry, manufacturers generally only report bands 2 through 7. This is due to repeatability issues in the first and 8th bands. Grills and diffusers tend to set their NC levels in bands 4 through 6. But for terminal units, the critical bands tend to be the 2nd and 3rd bands. These are the frequencies generated by electric fan motors and dampers. When a fan motor is running, you can be sure that the NC level will be set in the 2nd octave band, although it's possible that it could shift to the 3rd octave band at higher speeds. This fan noise tends to override any contribution from a primary inlet damper on a fan-powered unit. Proper sizing and selection of the primary inlet is critical to prevent noise issues. It might not be obvious to most people, but oversized dampers can cause just as many problems as undersized dampers. First off, don't be deceived by selection software and published data. If you keep bumping up the size of a damper for a given inlet pressure and airflow, you will see the sound levels drop. But that's not really the whole story. These sound levels that you're looking at are based on the unit operating at the design airflow. This is due to the fact that there's an unwritten law of acoustics that says the more air you move, the more noise you'll make. Unfortunately, that isn't necessarily true when dampers are oversized. As an oversized damper begins to modulate towards its minimum flow position, it can generate pure tone noise. This is due to the air jetting around the damper seals, causing them to vibrate. The amount of noise generated at various frequencies is dependent on the damper design, condition of the seals, roundness of the duct tube, and the exact pressure being applied. These are variables that no software can take into account, so the noise level can't be predicted at turn down. Don't fall into the trap of oversizing dampers. So how should VAV inlets be sized for low noise and low pressure drop? My golden rule is select inlets for a maximum inlet velocity as close to 2,000 feet per minute as possible without going over by much. I know that air moving down a duct at 2,000 feet per minute or less shouldn't self-generate noise, and by keeping my inlet velocity up at this level, I won't fall into the trap of oversizing inlets, and I will also avoid any airflow control issues at turn down. But what about inlets handling constant volume? Well, since there's no turn down to consider, it's okay to slightly oversize constant volume dampers in order to achieve lower sound levels. I still try to keep the inlet velocities between 1,000 and 2,000 feet per minute for a constant volume damper. Now that we know how to size our inlets, we need to look at sizing blowers for fan-powered terminals. I use different guidelines depending on the type of motor being selected. In the case of the older permanent split capacitor or PSC motors, I try to select in the top 25% of the flow range. I don't want to pick at the very top of the curve because I want to ensure some headroom for field adjustment. But I know that by keeping my selection in the top quarter of its range, the efficiency will be improved and the motor should run cool and provide much longer service life. It might surprise you to know that PSC motors operate better and longer the harder they work. PSC motors running at low speed against low discharge pressures tend to hum loud, run really hot, and they usually don't last very long. The newer electronically commutated motors, or ECMs, are a whole different game. I try to select ECMs in the bottom 50% of their operating range. Since they always run cool and they don't hum, they have no problem operating safely at lower speeds. By reducing the operating speed, we can reduce the sound level while maximizing the efficiency of these motors. Although ECMs have a minimum efficiency of 70 to 80% depending on who you talk to, they can actually achieve efficiencies in excess of 90% when operating at low speeds. While we're on the topic of fan-powered terminals, it's worth saying that it makes sense to limit both the minimum and maximum design airflows for these units. I'm often asked to select fan terminals to handle less than 200 CFM. I call that tiny fan box syndrome. It happens when a designer places a fan terminal in every space, including every closet and vestibule, regardless of size. To me, it makes no sense to place another fan into a ceiling plenum if it's not necessary. I would encourage serving these small spaces with single duct VAV terminals instead. Then there's the requests for fan terminals handling as much as 4,000 CFM. Well, that's just asking for trouble. It often means that a temperature control zone is too large, which leads to poor comfort when served by a single terminal unit. It also requires a very large unit that will likely create a concentrated noise source above the ceiling. These spaces would likely be better served by splitting the zone in half and using two smaller units, perhaps one handling the interior and the other handling the perimeter. My rule is to not try and move much more than 2,000 CFM through a fan-powered terminal unit. Now let's look at attenuators. Various types of attenuators are available for terminal units. Single duct terminals are typically available with discharge attenuators that are often nothing more than line ductwork. The amount of discharge attenuation they provide is strictly dependent on the type of lining. Softer, thicker linings tend to provide the lowest discharge sound levels. Of course, if you have lined ductwork downstream from a terminal unit, then an attenuator might not be necessary at all. Dual duct terminals often include optional mixer attenuators. Their purpose is to mix hot and cold air streams together, and this generates pressure drop and turbulence. This means that any attenuation provided is there just to reduce the noise level of the mixing process. So these are really mixers and not attenuators. Fan units are sometimes specified to include induction port attenuators, sometimes referred to as boots. These are often nothing more than a lined box with one side missing that simply blocks the line of sight to the blower. These are rarely effective and often only provide a reduction within the range of measurement error, typically not more than 1 to 2 dBs. Carefully designed induction port attenuators can be highly effective, but they can also be a design challenge. That's because the low-frequency sounds that we want to reduce are more difficult to attenuate. Now let's look at silencers. It's often tempting to install a silencer immediately downstream from a terminal unit to reduce discharge sound levels. Unfortunately, the results can be disappointing. The air coming off of a damper or being delivered from a blower will likely not be evenly distributed across the discharge ductwork and could result in noise generation inside a silencer. Silencers are tested with straight ductwork and even airflow on both sides, but this is very different from a close-coupled terminal unit application. The best advice is to place the silencer as far away as possible from the discharge of a terminal unit. Elbow silencers can be particularly effective. If a silencer is going to be provided as an option on a terminal unit, it must be tested on the terminal unit. Now let's look at an ideal installation. In order for a terminal unit to operate properly and provide the lowest possible sound levels, it's important that it be installed correctly. As you can see, we have a nice straight inlet duct approach sized for no more than 2,000 feet per minute velocity. We want to put the unit as high above the ceiling as access will allow, and of course we'd like to have a ceiling if at all possible. Sometimes, in the absence of a ceiling, partial ceiling panels, referred to as clouds, can provide some noise reduction immediately below a unit. Flexible connections, especially on fan units, on the inlet and discharge ducts, can break up any duct vibration and resulting sound. I'm often asked about spring isolators. They aren't really required, and the units are tested and rated with rigid hangers. It's also worth noting that direct drive fan motors typically include rubber isolation grommets to provide internal vibration isolation. We'd like to have at least 4 feet of line duct before our first diffuser takeoff. We typically want to size the discharge duct for no more than 1,000 foot per minute. Then we want to have good quality acoustical flex duct running out to the diffusers. You can think of flex duct as flexible silencer, but the length should be limited to no more than 5 feet, and it should be properly supported and managed so as not to create a poor inlet condition at the neck of the diffuser. So let's summarize what we've covered. Terminal units are performance rated in accordance with AHRI Standard 130. Sound power is the total sound energy generated, and sound pressure is what we hear and measure with instrumentation. Don't oversize VAV inlets. The amount of damper noise generated is dependent on the delta PS across the damper. Fan noise typically overrides damper noise in most terminal unit designs. Terminal units are performance rated in accordance with AHRI Standard 880. Beginning in 2012, AHRI Standard 880 began requiring end reflection losses, or ERL, to be added to all discharge sound power levels. Room NC levels should match the purpose of the room. Published NC levels are determined by applying the attenuations provided by AHRI Standard 885 Appendix E. And last but not least, proper installation is necessary to achieve the lowest possible sound levels. I think we covered everything that we intended to cover. I want to thank you for attending our webinar. Hopefully you've improved your understanding of terminal unit acoustics and will be able to use some of these concepts in your future ventures. Thank you and have a productive day.
Thanks, Randy. Now let's start the Q&A session.